Today what we're going to do is take a look at solutions, and solutions are going to be combining some of the stoichiometry, balancing equations, doing the conversions of moles to mass and mass to moles. So it's bringing a lot of this stuff together into one thing. And so to begin with, a solution. I remember somebody had a t-shirt. It said that alcohol is soluble in water, therefore alcohol is the solution. And I had to think about that for a second, and I think chemically that is correct. Is that correct, David? Yeah. I think it is, but it's not, it may not be good judgment, but I think it is good science. All right, so what is a solution? A solution is a homogeneous mixture. If you have two things that can mix together, such as sugar and water, salt and water, Kool-Aid and water, anything in water, if they mix together homogeneously, we would call this a solution. Now there are other solutions besides water, and brass is an example of that. Brass is a combination of a couple of different elements, and I'm trying to remember if that's copper and zinc. I don't remember off the top of my head, but it is technically a solution. It's two different substances mixed together and it's homogeneous. Stainless steel, we have iron and carbon, maybe a little bit of chromium mixed in there, and filtered air. So air, if we don't think of like little particles floating around like asbestos, it should be homogeneous, a mixture of nitrogen, oxygen, maybe a little bit of argon. Now an aqueous solution, typically this is water. Water is the solvent. And so that's where we get the aqueous from, and that's primarily what we will be using in general chemistry is aqueous solutions, things dissolved in water. And then we have concentrations, just how much stuff is dissolved in water. And this reminds me of when my sister and I would make Kool-Aid as little kids. She had this method for making Kool-Aid where she would take the pitcher, fill it up with water, throw the little packet of Kool-Aid in there, and then she would just add sugar until it tasted good. And the first few cups were all right, but by the time I got to it, there'd be like this pasty sludge that would come out of the bottom of the pitcher, and it was gross. Now when you have a solution where you cannot add any more stuff to it, like you add and add and add and you cannot add any more, we have a fancy term for that. Does anybody know what that fancy term is? Where you saturated, yeah. So saturated is when you have a solution where you have so much solute that it no longer goes into solution. Nicely done. That would be a saturated solution. Now, concentrations, we have different ways of measuring concentration. And so you might see milligrams per kilogram or milligrams per liter. We've already done parts per billion, I believe, when we did the bagel exercise. But the one that we really focus on is molarity. And so molarity is a big capital M. And this is moles per liter, and that's liters of solution here. So moles per liter. And we can solve for any one of these. And so this concentration, we could solve for that, it's just moles over liters, or we could solve for moles and say, well, okay, so if I just want moles here would then be equal to my concentration times my volume. Moles is equal to my concentration times the liters here. So we can solve for any one of these variables. And so that's about as complicated as it gets. So for example here, it says what is the molarity, or what is the concentration of an aqueous solution prepared by adding 36.5 grams of barium chloride to 750 milliliters of solution. So I'm trying to make this as complicated as I possibly can here. I've got 36.5 grams of barium chloride. Barium and chlorine. Barium and chlorine. Of course, what do you do with a dead chemist? You bury him. Okay, excellent. All right, good. We're awake. So barium and chlorine, some people are shaking their heads already. What's wrong with this? Barium chloride, it has barium, it has chlorine, but there's something wrong with this. There should be 2 chlorines. Okay. There should be 2 chlorines. And the reason for this is because if we look at our charges, or where we are on our periodic table, barium is a group 2 element, so that's going to be a 2 plus charge. Chlorine is a group 7, which is going to be a minus. And so then to balance out these charges, barium chloride becomes BaCl2. Okay. All right, so let's see here. It says prepare the solution, 36.5 grams of barium chloride. And let's see, this equation doesn't have grams in it. But I can convert grams. I can convert grams into moles. So if I take these grams here and I convert it to moles, so I take barium and 2 chlorines, add that together, 208.23 grams of barium chloride per mole of barium chloride. That will give me my moles. And so I ended up with 0.1753 moles of barium chloride. Now I have moles. So I have moles, and I could drop that in here. And then liters. Well, I don't have liters. I've got 750 milliliters. So how do I convert milliliters to liters? Divide by 1,000? Excellent. Okay, so I'm going to take my 750 milliliters, divide it by 1,000 milliliters per liter, and that's really just moving the decimal 3 spots. And so that gives me 0.7500 liters. Now I can just plug these numbers here into my equation up above. And so my moles here, I've got 0.1753 moles. And my volume is 0.7500 liters. And when I finish this, I end up with a concentration of, let's see here, 0.234 moles per liter. That'll be moles per liter is my concentration. And then I'm feeling pretty good about that, and that is barium chloride. Now, any questions on that? All right. Well, now this is where it gets a little bit, I guess, curious or a little bit odd. If we try to imagine what's happening here, we have a beaker, and oh, there, that's a nice beaker. Okay, and in that beaker we have our barium chloride, and we have a certain concentration. So this is 0.234 moles per liter barium chloride. That's my concentration. Now, this barium chloride, if it's in solution, then it breaks apart, and we end up with barium ions and chloride ions. And so these ions here, as they come apart, I'm just going to go like this and like this. My barium ions, I'm going to have barium 2 plus, and then I'm also going to have chloride ions. So I'll just go chloride ions like this. And the question is, how much of each of these do we have? And it gets a little tricky because my barium, for every barium chloride, I have 1 barium. So my concentration of barium ions here is equal to 0.234 moles per liter. And when we say concentration, we usually put brackets around it like this. It's kind of like what you did with polyatomic ions, and you put the charges on there. When you see the brackets like this, that's just saying concentration. So now the concentration of the chloride ions here, this gets a little trickier. Because the formula is BaCl2, when that dissolves, we end up with 2 chloride ions for every barium chloride formula unit. And so my concentration of chloride ions is going to be double this. So that'll be equal to 0.468 moles per liter. And then, if you were asked, what's the concentration of all of the ions? The concentration of all of the ions would be these here added together, and so that would be equal to 0.704 moles per liter. Now I'm writing moles per liter. People will also write this as 0.704 big capital M molar. It's the same thing. It's just putting the units in there. So the concentration of all of the ions is this. The concentration of the barium chloride is that. And that's where it gets a little confusing. And some people like scratch their head a little bit. It's kind of like if you were able to take bicycles and dissolve them in water. If you have 1 bicycle per bucket, I guess it would be a big bucket, maybe 1 bicycle per swimming pool, then what's the concentration of bicycle wheels? It would be twice the concentration of the bicycles because each bicycle has 2 wheels. So it's a little weird, but we're trying to wrap our minds around that. So here, let's try an example here. So what is the total concentration of ions in a 0.1 molar iron 3 sulfate solution? So give this one a try. You're going to have to write the formula for iron 3 sulfate. Iron 3 sulfate, you had this. Talk me through, how'd you do this? You put down an Fe for iron, and then parentheses SO4. So a 3 to the right, and then a 2 there. Okay, nicely done. Now, how did you come up with the 2 and the 3? Oh, you just had it memorized. Okay, and that works, right? Yeah.
You know what I was at, so I know iron has 3, so then I know the other.
So you know iron is a 3 plus, okay? So this here has to be a 3. So it's like whatever you have here, you're going to have down there, okay? And then, how did you know the 2?
Sulfate was a -2.
And we know that sulfate is a 2 minus. Okay, excellent. Now, the way I remember this one, I mean, this is just me personally, is this one here. Do we recognize this? That's sulfuric acid. I know that sulfuric acid is H2SO4. I know each hydrogen is a plus, and so then to balance this out, this has to be a 2 minus. That's just how I remember what the sulfate ion is. And you know, if you memorize, memorizing works. I mean, we have to for our polyatomic ions. Unfortunately, it's just not an easy way around it. Okay, so nicely done. Nicely done. So now with this, here's our formula, and it tells us that the concentration on this is equal to 0.10 molar. That's our concentration of all of that. But it asks us what's the concentration, total concentration of the ions. So when this gets into water and if it dissolves, how many ions do we have in the water? And so this comes apart, and we'll end up with a couple of irons. So an Fe and an Fe, and these will each be 2 plus, 2 plus. And then this sulfate here will end up with 3 of those. So SO4, 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 2 minus, 2 minus, 2 minus. Okay, so this will break apart into these 5 things. Yes? Because it's 3 plus. Thank you. Thank you. Okay. Yes. Yes, thank you for catching that. 3 plus. Okay. We'll make sure to edit that so I don't make mistakes when this goes online. Okay, good. All right, awesome. I look so good when everything's edited. Yeah. We've changed the voice so I sound like Liam Neeson. I have a certain set of skills. I will find you. Yes. Okay. Thank you. So we have 5 possible ions here, and each one of them has the concentration of this 0.1 molar. And so when we add this all together, here, this is going to give us a final concentration here of 0.50 molar. That's the total concentration of all of the ions. Okay. All right. Now, making these solutions, we can also make dilutions. So a dilution is where you just add more of the solvent, and typically this is water. And this doesn't change the number of particles that are there. And so, for example, in this slide here, we've got these test tubes, and there's 5 different green particles floating around. And it doesn't matter if we add more water, it doesn't change the number of particles. And this is important because this allows us to do some fancy math with doing dilutions. So adding dilutions, we're just adding more solvent, we're making it less concentrated, and we don't change the number of particles that are there. And because of that, we get this formula here. Now this formula tells us that the moles of the solute in the stock solution, or our concentrated solution that we pull off the shelf, is equal to the moles of the solute in our diluent, or what has been diluted. And so our formula here is we have our volume times our concentration is equal to our volume times our concentration. So this is before and this is after. So this is our concentrated solution, and this is here after we added our water. We haven't changed the number of particles, we've really just changed the volume. I love this chapter because the only formulas in this chapter is just this and then that one over there, right? And these formulas don't look too bad. It's not too bad. If you've taken physics, you can see some nasty, goofy looking formulas here, right? This is not so bad. So here's the question here. Hydrochloric acid is obtained in a 12 molar stock solution, very concentrated hydrochloric acid. It says what volume of stock solution is required to make 500 milliliters of a 0.145 molar dilute solution. And there's lots of numbers in there, and it seems really complicated, but fortunately our formula is just this here. This V1 M1 is equal to V2 M2. And what we're trying to find here is, let's see, it says here what volume of stock solution. So this is our concentrated solution. We're trying to find this right here. And so we can then look at what our numbers are here. So I'm going to rearrange this equation and solve for V1. And so that's equal to V2 over M2 divided by M1. And so this right here is when it's diluted. And so my volume, when I'm done, it tells me here is 500 milliliters. Now 500 milliliters, I can convert that into liters by saying that's 0.500 liters times my concentration here when I'm done is 0.145 molar. And what I started with was 12 molar. And then when I'm done, I end up with how much of the stock solution I needed here. And this is 6.04 milliliters. Wait a minute, what am I doing here? I don't have milliliters in this. Oh, okay. I think I skipped, maybe I skipped a step here. Okay. If we left it in, I'm just going to write over here. If we left this in milliliters, 500 milliliters like this, if we left it in milliliters, this would be our answer. If I converted into liters like I did here, then my answer would be much smaller. This would be 0.006, all right? 1, 2, 3 liters. Did I do the math right? I struggle to do math in my head when people are looking at me. So I have a superpower. Did you know that? I can turn invisible, but you can't watch, can't look. Okay, right? Close your eyes. Oh, I'm invisible.